Okay, I'm going to talk about section 3.3. This section will be done in two parts. Today's the first part. So this is increasing and decreasing in the first derivative test. Today we'll be focusing on increasing and decreasing. And then when we do part two, we'll do the first derivative test. These are closely connected, so that's why we do them sort of as one topic. Okay. Increasing and decreasing is an idea that has been introduced to you in earlier classes. You should be able to tell from a graph whether a function is increasing or decreasing. You know, pretty straightforward here. You know, if I have a function like this, we're increasing when the values as we go from left to right are going up essentially, or a value on the left is less than the value on the right. And conversely, if we have a function that's decreasing left to right, a value on the left is going to be greater than a value on the right. But I think for the most part, we think of this very intuitively. If the function is increasing, it means it's going up left to right. If it's decreasing, it means it's going down left to right. Today, we're going to be able to indicate that or find these intervals using calculus. Okay. So tests for increasing and decreasing intervals. Let f be a function that is continuous on the closed interval a to b and differentiable on the open a to b. I will tell you that just like with the mean value theorem, typically we're dealing with functions that are going to be differentiable throughout the values we're looking for. This is just opening the door for a function, you know, that has a sharpness here we could still consider on that interval, including that endpoint, but that would be more rare, okay? So don't get too hung up on why we do the closed versus the open. Okay, so if f prime is greater than 0 on the open interval a to b, then we say f is increasing on the closed a to b. So if f prime is greater than 0, so we want to think about what that means. That means the slope is positive. So if the slope is positive, right, then we're increasing. So it's pretty straightforward. Once again, there's a little bit of the true on the open, which gives us the closed. I will tell you that on the AP test, a lot of times that's not an issue because they'll ask for the open interval. And this is something we'll discuss a little bit when we're doing examples in class. And then on the other side of this, if f prime is less than 0 on the open interval a to b, then we would say f is decreasing on the closed interval a to b. So once again, if f prime is less than 0, that means all my slopes are negative. So once again, we're decreasing. So it's kind of an intuitive thing. Okay, so now I'm going to do a couple examples demonstrating how we can use these derivatives to determine when a function is increasing or decreasing. Okay, example 1, f of x equals x squared. We're going to find intervals of increasing and decreasing. So I wanted to start with a function that we actually all know what this looks like, and we could actually do this without calculus, so then we can kind of see what's happening. So really basic function here, f of x equals x squared, parent function for our parabolas. Very clearly we can say the interval that it's decreasing is negative infinity to 0, including 0 if we're using closed endpoints. And then we can also say it's increasing from 0 closed endpoints to infinity. So let's see what that looks like as far as the calculus goes, just to confirm what we already know. So f prime of x equals 2x equals 0. So the first thing we do when we're finding intervals of increasing and decreasing is we find critical points. So critical points, once again, is anywhere where the derivative is 0, or perhaps the derivative does not exist. This is the only places where our derivative can change from positive to negative, assuming that it's continuous. If there is some sort of break in continuity, then we would also have to consider those breaks as possibilities for the derivative going from positive and negative. So just think about it. In order for our derivative to go from positive to negative, one of these two things have to happen. So we can find all our intervals if we first start when the derivative is equal 0. So once again, f prime of x equals 2x. So clearly x equals 0 is our only critical point of that. with any polynomial, and this is one thing that is pretty nice, whenever we're working on polynomials, we want to keep in mind that we don't have to consider, points where there's domain issues. We don't have to worry about when f prime doesn't exist, because polynomials, the functions are always continuous, they're always differentiable. So they're really nice to work with. They're what we call well-behaved functions. Okay, so now what I do is I do a number line, and this one's really basic, but when we get to harder problems, this is going to be a little bit trickier, which we'll see later. So I'm going to put on my one critical point, and keep in mind we're just testing this one value 2x. So I'm going to pick test values. Pick any value you want to the left of 0. Let's pick -1. Pick any value you want to the right of 0. That's 1. What ends up happening if we pick one test point, since we know all of the places where we can switch, for whatever value you get for your derivative here, that will be true for all the values in that interval. Same is true for the test point here. The value we get for our derivative here will be the same for all the values over here. Otherwise, we would get another 0 or another f prime equals 0. So if I plug -1 into 2x, I actually don't care about what the exact value is. All I care about is whether it's negative or positive. So it's negative. If I plug 1 into 2x, I get positive. So what that means is my function is decreasing to 0 and increasing here, which we know because we know what this thing looks like. So let's write out how we would answer this question. So we would say f prime, or f is decreasing on, and we're going to go with the stronger statement here, -infinity to 0, including the 0. Quite often we go with the weaker statement, which means the open intervals, but I want to talk about this a little bit. F is decreasing on -infinity to 0, and that is because f prime is less than 0 on, and then -infinity to 0. And we would say that f is increasing on, once again, we'll go with the stronger statement, 0 to infinity, and that is because f prime is greater than 0 on, and then 0 to infinity. Now, what sometimes confuses people is technically, if we go with the broadest, the closed interval, 0 actually gets included in both intervals. F is decreasing from -infinity to 0. If you think about this, if I just focus to 0, yes, it's decreasing the entire time because the value here is less than any point to the left of it. If you take the closest point to the left of it, it doesn't exist because you can always get closer. But just think of a point just a little bit to the left of it, that f of 0 is certainly going to be less than that. And on the other side, if I just look on the right of that, the same is true for increasing. F of 0 is going to be less than the point of, let's say, anything to the right of that. F of 0.1, f of 1, it doesn't really matter. So technically 0 can get included in the interval of decreasing. It can also get included in the interval of increasing. However, to sort of save the confusion and also stating the domain again, or the interval again, often it's easier just to go with the open interval, and that's going to be more common than going with the closed interval. But just to talk about, or just to sort of see that technically 0 can be included in both, is why I use this example. Okay, so I want to start with this example because it's something we all know and we're all used to, and now we can confirm that what we see from the derivative is correct. At this point, you're probably thinking, wow, this is all overkill for a graph I could just have graphed and then come up with the question. So now I want to do an example of one that you probably would not be able to do without calculus. Okay, example 2, once again, we're still in the realm of polynomials, so we don't have to worry about domain issues or differentiability issues. We have the function x to the 4th minus 8x squared. But let me point out, this is probably not one you're able to graph without a calculator, so it's certainly one we're going to need calculus. So once again, the first thing I need to do is I need to find all critical points. I need to find when it's switching from a derivative that's positive to negative or vice versa to determine intervals of increasing or decreasing. So the first thing I'm going to do with this is I'm going to take the derivative. So f prime of x is equal 4x to the 3rd minus 16x, and I want to know when that's equal 0. Okay, so we're going to use the zero product property, so we're going to factor out 4x, which leave me with x squared minus 4 inside, and then of course I can factor this again, so I get 4x, x plus 2, x minus 2 equals 0. So I actually have 3 critical points, so x equals 0, x equals 0, x equals negative 2, and did I do that correctly? Okay, so now I'm going to make my number line, and all of my critical points, so these are all my critical points, negative 2, 0, and 2 go on my number line. Now what I'm interested in is when my derivative is positive or negative. I don't really want to work with this thing because with the x to the cubed and the 16x, I'm going to have very, very large numbers. So this is kind of a trick I can do. All I really care is whether the thing is positive or negative. So we're multiplying 3 factors together. So if 2 of those factors are positive and 1 is negative, then I know it's going to be negative. If 2 of them are negative and 1 is positive, I'm going to have positive. So I can just play this game of counting negatives, right? So if there's an even amount of negative factors, then the derivative will be positive. If there's an odd amount of negative factors, then our derivative will be negative. So all I'm going to do here is I'm going to line up all my factors. So 4x, x plus 2, and x minus 2. And now I'm going to do the same thing I did with the last one. I'm going to pick those test points. Any value over here, whichever one is easiest. So I'm going to choose negative 3. It really doesn't make a difference. I'll choose negative 1 in here, 1 in here, and then 3 here. So now if I plug negative 3 in this, I get negative, negative. So in other words, negative 3 times 4 is negative 12. I don't care about the negative 12, I just care that's negative. Negative 3 plus 2 gives me a negative, that's all I care about. Negative 3 goes in here, that's negative. So now that means that my 3 factors, all of them are negative. So if I multiply a negative times a negative times a negative, that means my result will be negative because I have an odd amount of negatives. Okay, now negative 1, that's going to be a negative, that is going to be a positive, and then that is going to be a negative. So this is going to be a positive. 1, positive, positive, negative. And 3, that's going to be positive, positive, positive. So this one, we have an odd amount of negatives, so this is going to be a negative result, and this is going to be a positive result. Now this alternating pattern we see is a common pattern, but it doesn't always happen, so don't assume that you're always going to see that, because there are some things that will make it go positive to positive or negative to negative. Okay, so our intervals of increasing. So f is increasing. I'm going to go with the weaker statement here. That allows us to be a little bit lazier with our justification. I will tell on the AP test, they don't really specify that you always have to go with the closed interval, so I'll typically go with the open interval unless there's a reason not to. So f is increasing whenever f prime is positive, so negative 2 to 0. I'm going to go open on both, and 2 to infinity. Open on both, obviously open to infinity, and that is because, and that's just because f prime is greater than 0. Okay? And then finally, f is decreasing. Once again, I'm looking for when our derivative is negative, so that's going to be negative infinity to negative 2, and then 0 to 2. And that is because f prime is less than 0. Okay? So this sign chart thing, I will tell you, this usually takes people a little while to sort of get the hang of, but it will make your arithmetic a lot easier. We don't necessarily want to be taking these, for instance, if I took negative 3 and plugged into this, not that it's impossible, but it's definitely a little bit more annoying than using these factors. Okay. So let's do one more example. And that will be it for this video. And then the next video we'll talk about first derivative test. Okay, example 3. We have the function f of x equals x to the 2/3 power minus x. And we want to know when it's increasing or decreasing. Now let me point out, this function is not a polynomial. It is always going to be continuous, and if you need to think about this, keep in mind x to the 2/3 power means we're going to take the cube root of x and then square it, or vice versa. But regardless of that, this thing's going to be fine because all the values that I plug into this are going to be fine. The cube root of a negative number is perfectly fine. It's only when we have an even root. So the domain is going to be all reals. This thing's always continuous. But it will have a differentiability issue, which we'll see when we take the derivative. Okay, so let's look for those critical points. So f prime of x is equal to 2/3 x to the negative 1/3 minus 1. We want to know when that's equal to 0. Now, when we were actually churning out derivatives, we would leave things like this. But now we want to simplify because we have to work with this. We have to figure out what's going on here. So I'm going to rewrite this thing as 2/3, and then realize that negative exponent, that moves to the denominator. I'm going to call that the cube root minus 1 equals 0. So right away I see a critical point. As I mentioned, all values are fine here, but we see we get a 0 in the denominator. So that means we have a crit point at x equals 0 because f prime of 0 does not exist. Now we also have to find when it's equal 0, so we have to do a little algebra here. So let's go ahead and do that. So I'm going to move the 1 to the other side. So I'll have 2 over the cube root of x is equal 1. And now what I can do is multiply both sides by the cube root of x. So that is going to give me 2 times, or let's do, I think I lost the 3. So 3 cube root of x, sorry, it's a little bit messy. I'm just moving this one on the other side. So let me go ahead and just finish this up. So this will give me 2 equals 3 times the cube root of x. So then I get 2/3 equals the cube root of x. Now, how do I undo taking the cube root of something? I raise it to the 3rd power. So I get x is equal to 2 to the 3rd power is 8. And then 3 to the 3rd power is 27. Okay, so this is a kind of small number here. You know, if you think about it, if this was 9 over 27, it would be 1/9. So it's almost 1/9. It's a little bit less than 1/9. Okay, so let's go ahead and do our number line here. Okay, so this is where it gets a little bit tricky because we got to play around with this value. So here are our critical points. X equals 0 because f prime doesn't exist. And then we also have a critical point at x equals 8 over 27, and that is because f prime is equal to 0. So 0 and 8 over 27. Now this one is definitely not as nice as the last one where I could just line up the factors. I do want to figure out what the value of this is, but there's no really nice way to break it down. The good news is I don't have to find exact values. Now, when I choose my test points, I want to be very careful. I actually want to choose test points that I can take the cube root of. So for instance, over here, this is going to be very easy because I can choose -1. I can take the cube root of -1. And on this side, 8 over 27, I can choose 1. Now, what gets a little tricky is I want to choose something in there. 8 over 27, like I said, is less than 1/9. So what I want to realize is that if I choose something like 1 over 27, I'm going to be able to take the cube root of that, and we know that's less than that value. Okay, so I think 1 over 27 is about as good as we can do there. It's not wonderful, but we can figure it out. So if I plug negative in here, right, the negative will be retained because we're taking the cube root. So this is going to be -2/3 minus 1, so that's going to be negative, okay? Now, 127, we might have to do a little arithmetic here. The cube root of 1 over 27 is 1/3, right? So this is going to be 1/3. 1/3 times 3 is going to give us 1, so this is 2 minus 1, so this will be positive. Okay, and then the final value, plug this in, we're going to get 2/3 minus 1 again, so that's going to be negative. Okay, so a little bit harder to deal with, but I think we can figure it out. So our intervals of increasing here is going to be 0, and I get a little lazy there, I just show an upward arrow, to 8/27. Once again, I'm going with this open interval. That way I can be kind of quick with our, and that is quick with our justification, and that is because f prime is greater than 0. We're decreasing negative infinity to 0, and then 8/27 to infinity, and that is because f prime is less than 0. Okay, so that is the first part of our 3.3 video. So that is how we determine when intervals are increasing, decreasing. Next time we'll do the first derivative test.